Hello. Let's discuss big O notation. It is a way to describe how your algorithm handles increasing amounts of data. So, for example, let's imagine we have a simple algorithm that just takes the second element of an array. So let's say I have an array or a list or whatever you want to call it, and I want to access the second element. At this point, we have 3 elements in there, so n is equal to 3. If I increase the size of this array and add 1 million elements, I will still only require one step to access the second value. I hope you understand that. So this is called constant time complexity, and on our graph it will look something like this, and it's denoted as O of a constant. So in our case it was one step, so we put in 1. The next time complexity is called logarithmic time, and it looks just like a logarithm, and we denote it as O log n. One example of such an algorithm could be binary search. As we get more data, we need to take more time to search our dataset, and that's the case quite often. Next, we have linear time, which is basically a line, and we denote it as O of n. One example of such algorithm could be looping through a list of elements. So let's say we have an array, just like before. We want to go through all of the elements in the array. So let's say our n is 3. To loop through all of them, we need 3 steps. Here's the first one, second one, third one, right? If the array would be of size 30, we would need 30 little steps to go through all of the elements. So this is called linear complexity, because adding one data point adds one step to the complexity of the algorithm. Next, we are entering the field of quite inefficient algorithms, and now we have quasi-linear time. So it's similar to these two. It's like a combination of them, and it looks like an inverse logarithm, and you denote it as n log n. One example could be quicksort, heap sort, merge sort, and yeah, it's quite inefficient. I hope you understand the pattern that is going on. We are always using math to describe how this function we are drawing reacts to the increase of data points. And finally, the least efficient algorithms are quadratic time or exponential time, and they look just like an exponential function. So it's a steep line upwards, and we denote it as something like this, n squared, for example. And one example of an O(n) squared algorithm could be a very popular sorting algorithm, usually taught to people who learn computer science. I don't really know why, maybe because it's just simple. It's called bubble sort, and I'm pretty sure you have heard of it. So that would be it. I have drawn here some different time complexities: constant time, logarithmic time, linear time, quasi-linear time, and exponential time. And they are from most efficient, starting from here, to least efficient, going there. So that would be everything. I hope you learned something, and if you did, that's really amazing. Hope to see you next time. If you have any questions, just ask in the comments. Bye bye.